years to come.
Great, I don't have to work next year. I can just show people my videos. It's so easy. All right, so I didn't quite get through all the exams because you guys didn't listen to me. I asked you guys not to get things wrong, right? If you guys just get 100 and just go through. I had to fix some stuff for my Gen Chem class, and I've got an exam for them tomorrow, so let's work on that. But I'm about halfway done. I'll try and get it to you guys Wednesday, but I don't know how lazy I'll become between now and then. Just being honest, but I promise I'll get it for you guys this week, all right? Like I said, I'm about halfway there, and then we'll get that wrapped up. But anyway, we were making our way through the radical chapter here, and we have the one mechanism that we have to deal with, and that mechanism has the three parts to it, right? We have the formation of radicals, which we call the initiation. One radical turns into another, which is the propagation, and then at the end, two radicals come together, and that's the termination. Right? So now we have a way of adding a functional group to an alkane. Okay? But we have to go back and discuss a couple details and figure out a couple of this and that's along the way, I guess, right? How does it work? Why does it work? And what are the limitations and these kind of things with it, right? That's kind of the other end of it. But anyway, so this is the mechanism to know for any radicals here. Okay? All right, so I believe, let's see, what was the question that I originally asked? Yeah. Okay. So if, oops. So if we have this molecule here, and we try and do a radical halogenation, okay? If we try to do a halogenation reaction here, right, we're going to add a bromine to the most stable location for a radical intermediate, okay? You guys catch what I'm saying with this? So when we go through and do this reaction, we're going to add the bromine to the most stable position for a radical intermediate. Got it? Now you guys already understood this. Why? Because that's how every reaction works, right? Every reaction works by you make the most stable intermediate, and then the incoming group gets added to that, okay? That's how our SN1 reactions work. You guys generate a carbocation, and we have to do some shifts or whatever it might be, and it generates the most stable intermediate, right? Thank you. Everyone else, I thought this was Greek, right? Right? You make the most stable intermediate, and that's the most reactive one. So what does this tell you? What does this result here tell you? That the most stable intermediate is formed at the tertiary position, right? Oh, gee, where have we seen situations like that before? Where intermediates are most stable at the most substituted positions. Okay. So a carbocation. So radicals in general, I'll give you the vision at the end. Right? Radicals in general follow the same rules as carbocations. Okay? Where the most stable intermediate for a radical is usually the same as where we would generate a carbocation. Okay? Now there's going to be some differences, sort of, right? There's going to be some subtlety, sort of, but in general, that's the kind of the idea to follow, to understand. Okay? Here's caveat number one. That works for bromine. Okay? When I do my radical halogenation with bromine, it's relatively well behaved. It'll only add a single bromine. Okay? And life goes on, and we can get what we want. Radical halogenation with chlorine is not quite as, let's say, well controlled. Okay? Radical halogenation with chlorine works, except chlorine has loose morals. Okay? It's just going to react with everything. Okay? Halogenation with chlorine kind of just goes after the statistically most relevant hydrogens. What I mean is this, okay? So our two methyl groups here, right, there's 6 hydrogens there that could be abstracted and could be reacted with the chlorine, okay? The methyl groups are going to react faster, right, or going to react more often than the non-methyl groups are. So typically we'll see halogenation with chlorine kind of hit the methyl groups first. That doesn't mean that it's necessarily going to be the major product, it's just we can't really stop that from happening. Now the stability and the reactivity of radicals is dependent on, hold on, let me clarify this. The reactivity of radicals is based on the stability of that radical itself. The more stable a radical is, then the more it can kind of just wait and find the right hydrogen, okay? But with chlorine's loose morals, it doesn't want to wait. It's going to find whatever it comes into contact with first. That's kind of the point here. So as soon as it sees a hydrogen, it's going to snap it, okay? And then it's going to add a chlorine there. So really we don't want to use chlorine here to do our reactions with. Kind of makes a mess, okay? A somewhat controllable mess, but mostly a mess. But bromine, on the other hand, behaves very nicely. So we will typically have no problems adding bromine to the most stable position for a radical to form. Right? Right. You guys catch what I'm saying with this? Where a radical gets added to the most stable position. Okay? Okay. So, first thing to recognize is that. Okay. Second thing, let's go through, or why don't you guys go through, and draw me the mechanism for that reaction. Working in this building is like having malaria. Like the first room I'm in is freezing. I come in here and sweating. It's no consistency. trick you guys on this one. I see a lot of 9s and 9 out of 10s. True. Hopefully that's bad. Is the mechanism going to be any different for the one in blue? No, right? That's the wonderful thing about mechanisms. They're the same no matter what, right? Right now you're on a 0 for 10. You started out with that's 5 bonds to that carbon is what you start out with, right? Yeah, don't do that. No hydrogen there. Okay, where's your mechanism? Well, I know, I'm talking about your notes. Uh-oh. Don't change the mechanism. Like a -1 on it. Gonna take more points off. And don't change the rules though. Right? Look for your most substituted carbon with a hydrogen on it, right? With a hydrogen. And that works from there. Okay. Don't add it. Now you've got 5 bonds to that carbon. Okay. 9 out of 10. But so now you have to go. -1. Don't react. Aromatic hydrogens. We'll do that this second semester. For now, they're the sacred cow. Right? We'll just leave them be. We'll just leave them be, and we won't do anything with them. Not a bad thought, but we won't be dealing with aromatic hydrogens this semester. No. Don't react our aromatic rings. Don't react our benzene rings. Don't worry, minions. That will come soon. Not yet. Okay, 9 out of 10. Okay. Now look for the most substituted carbon with hydrogens. And then work from there. So, question. Where is my most stable carbocation going to go? Great, we don't form a carbocation. You guys get the question I'm asking? Are you guys more comfortable dealing with carbocations at this point? No. Where would the most stable carbocation form?
Secondary.
Okay, we have only secondary carbons here. Well, we have two different secondary carbons, right? Got that one, and we got that one, right? Okay. It could form on both, except it won't.
Will it prefer to form closer to the ring because the ring can do resin?
Right? So remember, when you're dealing with radicals, we basically treat them like carbocations. We have to stabilize them in some way, right? Can we draw resonance structures with radicals? Sure, right? What's a resonance structure? It's just a movement of electrons, right? Can we move a radical around? Sure. Can you guys draw a resonance structure for a radical? I bet you guys can, right? Watch. Can you guys draw me a resonance structure? Everyone bet, say yes.
Yes.
Okay. Jason. I didn't hear it. Can you guys draw me a resonance structure here? Sure. Okay. How would it be different if I had a radical there instead? We're not moving two electrons as with the first there, right? But we're moving what? One at a time. Okay, we know here our resonance structure would have to end up looking like that. Got it? So we move our pi bond over. So what we know we have to do here is move our pi bond here and move the radical there. Got it? So how do we do that? This comes in, that comes in, that goes there. Right? Got it? It's pretty much the same thing, except we have to draw 3 arrows because we have 3 separate electrons to move around. Got it? So can you draw resonance structures with radicals? Yes. Should we look to stabilize radical intermediates? Absolutely. How do we stabilize them? Well, essentially, we have the same ideas as with carbocations. Okay, resonance and electronegativity and blah, 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 blah. All right? Although in reality, radicals aren't as influenced by, let me put it this way, they're probably mostly influenced by resonance structures, okay? They do behave a little bit differently, so I don't want to push the example too hard here, but look for resonance structures is what I'm trying to tell you, okay? Got it? So how should we treat our intermediates for radicals? So what's my product going to be? What's my product going to be up here in the blue reaction? Would. Except, how should we treat our intermediates? Go ahead.
Will it initially be on the green one and then move down to the benzene?
We're not going to see that happen.
Well, if it was a carbocation and then a rearrangement would happen.
It's going to form at the green one first. Right? It forms at the most stable position. I'll draw you the product, then you guys are going to, okay? So get it ready. Get your groans ready. What is my product? Nine out of 10. Got him again, right? So just like with a carbocation, right, these radicals will form racemic mixtures, okay? They will form at the most stable position. We can draw resonance with them, but they are planar intermediates. And so they're going to form racemic mixtures, okay? Now, I'm going to show you guys what not to do, okay? You guys have a very powerful tool. Now you guys can add a bromine to the most stable position on an alkane. But radicals don't behave all that well with other functional groups, okay? So we have to be very careful about what else is around. Sometimes they behave okay. So we have to be very careful, especially with alcohols. Radicals and alcohols, you're going to end up doing some weird stuff, okay? But one thing that I always end up seeing is you guys are like, aha, I've got the perfect plan. Okay? What I see quite frequently happening is you guys try to do something like this. Okay? It's like, I need to put a bromine, for whatever reason, on the same carbon where I see an alcohol. Question, how many times have we seen that setup for an alcohol and a halogen? All semester long. How many times have we ever seen a halogen and an alcohol on the same carbon? Never. So what do you guys think? When is that ever going to happen? It's not. Now, we don't necessarily know why, although you guys kind of do because we've talked about it. Bromine is a good leaving group, right? And carbon and oxygen are bestest buds. So that is just a desperate reason to make a carbon-oxygen double bond. This will very easily, excuse me, very easily kick off that bromine and form a carbon-oxygen double bond, okay? You're not gonna isolate that is what I'm telling you. So don't do that. In fact, I don't even know if that would form all that well under these conditions. Because that hydrogen on that oxygen there is more reactive than that hydrogen on that carbon, okay? So you probably would end up plucking away that alcohol hydrogen instead of this, okay? So what I'm saying is your radical reactions are usually going to be your first reactions in a sequence of synthesis to avoid any of these side reactions that happen. Everybody catch that. So if maybe there might be an exam or something, we're asking you guys to do synthesis, and you have to do a radical, it's probably going to be one of your first steps that you guys do. Just as an exam. Who knows? Catching what I'm saying? But radicals do behave well with certain types of functional groups. You know that? For instance, what would likely be the products for this reaction? Products. Not Carlson. weren't wrong with that, right? That those do form, but. Interesting thought, but I mean, that's what's gonna happen in this case. So, interesting thing, hang on to that, but work through the radical. You're not necessarily wrong, and we'll talk about that in a second. That is a product. You're right. What else? Okay. Right, but what else could form? Good? How did we get that? Okay. Break apart. Okay. Oops. Boom. Behold, an intermediate. What's so special about this radical though?
It's next to the bond.
Hmm?
It's next to the bond. So resonance.
Okay. Remember, we're always looking to make the most stable intermediate, whether it's a cation or a radical. Can we stabilize this? Sure. How can we stabilize it? Through resonance. Got it? So we can draw a resonance structure. I don't know what my computer was doing there. Right? We can draw a resonance structure wherein we generate this. Correct? So now can we see how we get to both of those products up there? Which one's going to be the major product? Maybe, right? Here we have the most stable radical, but we've got the less stable alkene, right? Here we've got the more stable alkene, but the less stable radical. You get what I'm saying? Remember, alkene stability is the more substituted, right? So it's a little bit of a toss-up. I would probably say the first one's the more dominant product. Okay? But I'd have to give you guys some other information to kind of knock that out there, right, to see which one exactly is. But there's still a product that gets formed. You guys know what it is? What is HV? H nu? Energy, right? If we add energy into a reaction, what happens? What speeds up? Everything. Got it? So what's the product that I'm missing?
Pi bond or something?
I probably can, right? What's the missing product here? The missing product here is what? going through our sumo mechanism, right? Does every one of the bromines turn into a radical and magically go through that mechanism nice and easy and neat? No, right? Can some of that bromine just hit that pi bond and go through and react using the sumo mechanism? The answer is absolutely, right?
Dr. H.
Yep.
I thought that halogenation could only happen when it was like cold and dark.
No. What I said is we need to keep it cold and dark to prefer the halogenation, right? Because as soon as you add energy into it, then we start to break things apart to the radicals, right? But it still can do halogenation, okay? There's going to be a lot more competition. So just like we have SN1 competing with SN2 and E1 and E2, right? We have certain conditions that we need to put things in to prefer one reaction over the other. It's the exact same thing here. If we want to shut down a radical mechanism, guess what we do? We keep things cold and we keep it in the dark, okay? If we want to promote a radical reaction, then we have to heat things up and shine light on it. Got it? But remember, as soon as you add energy into something, every reaction is going to go faster. Dr. H, I desperately want to do a radical reaction, but I don't want to do my halogenation. Well, then what we need to do is get rid of our Br2 as the source of our bromine radicals and give it something else, okay? And the something else then, we have a different reagent, is something called NBS. N-bromosuccinimide is what it's called. N-bromosuccinimide, if I remember correctly. Ooh, that's garbage. Let's try this again without terrible drawings. Okay. There's our buddy N-bromosuccinimide. I believe that I miss a double bond. Hang on a second. Let me double check. I think I did because I don't make mistakes, but of course. All right. Sorry, I thought I had left off a double bond there in the carbon, but down. Okay, so there's our buddy N-bromosuccinimide. It's a great source of bromine radicals, okay, without using Br2. Now, Br2 has some problems with it. The first problem is it sucks, okay? It's a gas that's orange, and just as soon as you open up the bottle, it's a liquid that easily turns into a gas, I should say. And it just like spews orange vapors everywhere that corrodes everything. And if you breathe it in, you're dead, so that's not good. Well, some days, okay. Right? But it's just difficult to control, is what it is. NBS, on the other hand, is a nice white powder that you can measure out, and you can buy it by the kilogram. You don't have to worry about all that stuff. So NBS is usually the way that we do these types of reactions in the lab. It's a very, very, very common reagent, okay? It's one of these reagents that are in pretty much every organic lab that does synthesis, okay? So that's what we end up using. And because we don't have Br2 around, we can't go through the sumo mechanism, and we don't end up with that product there, okay? Because remember, to do the sumo mechanism, we have to have that dispersion forming on one of the halogens, right, in the compound that we have. And then we can start to do the sumo, okay? But this N-bromine bond here is weak, and it just breaks apart into two radicals. And so that's essentially what happens, is what it is, okay? Cool. And then we just got some Br radical floating around, and it goes through and does its thing. So how do we get this set up? How do we do this? Okay. And we usually add some HV to it, right? go through and do what's known as allylic halogenation. Allylic halogenation. Now an allele, or an allylic carbon, is the carbon that is next door to a double bond, right? A carbon that is next door to a double bond. That is an allylic carbon. Now for those of you guys who are super duper attentive, right? You'll notice what? We have two allylic carbons, right? That's right, Dr. Rachel. But remember, when we're going through and forming our intermediate, right? We're going to form the most stable one. Okay? But now we're going to start paying attention to those allylic positions. The carbons that are next door to the double bonds. Now you guys have always been paying attention to those. I just never drew attention to them. Why? Well, where would you guys make the most stable carbocation here? Well, you make it next door to the pi bond so that what? You could draw resonance structures with it, right? It's the same thing here, it's no different. And don't forget that if you have a carbon, right? Or if you form a carbon at the end there, you form a receiving mixture. When you need to put a double bond, when you need to put a halogen next door to a double bond, NBS is the way to go. We shut down, or we basically get rid of that sumo mechanism. We don't have to worry about the competition with that. Okay? Good. More. We demand more. More information. Okay, so now, go ahead, what's up?
Oh, no, sorry, I was.
Oh, okay. So, you don't, I thought you had a, man, and ready for a good question, all right. Just look, if you guys don't want to learn more, you just have to like stall me, right? So it was, Dr. H, what's a carbon? I remember one of my favorite emails ever to a professor, this wasn't here. This was, it was before exam 3 in general chemistry. And if you guys remember, exam 3 in general chemistry is, you guys have just learned how to do your Lewis structures, and you learned about molecular orbital theory, you knew what the geometries were. You guys remember when things were easy, but you thought they were hard too? And now you're here, right? But anyway, my favorite question ever was, I got an email from a student, and Dr. H, I'm working through studying for exam number 3 in general chemistry. And I wonder if you could explain to me what an electron is. Oh, brother. All right, here I go. So, I guess the point of that story is also, please don't wait until the end to ask me these questions if they're right. Just come see me. You guys are good at this, right? But just to let you know, I'm always here to help. What's up?
I actually have a question. Why did we do
What's an electron? Is that what you said? What's up?
Why don't we show the wedge on the?
Because I'm showing that's a carbon, right?
Would we technically write the dash version too?
Well, that's what the plus EN stands for. Plus EN, right? Yeah. So your wedge or dash, either one, right? Just show me that it's a carbon. Cool. All right. So a little bit of review, right? Of course. Ooh. Sorry, let's do that. strong acid, alkene. Alkene grabs the hydrogen under acidic conditions. And logically, the formation of a carbocation is probably going to happen. So we check for shifts and rearrangements and all that kind of stuff. And we end up doing Markovnikov addition of a bromine to an alkene. Right? Nice, easy, no stupid single-headed arrows. Life is good, right? Okay? Not always useful, right? Sometimes we need to put a bromine in a different place. So, this is our buddy H2O2, right? So now we put HBr in with a peroxide. Peroxide. Now, what did we say about peroxides? What are these flags for us to pay attention to? When we see a peroxide in a reaction,
Is there any water? Is
Hmm?
there on the substituted?
we usually end up adding things to the less substituted side, right? So we have this example here where we add a bromine to the less substituted side. And we have our example of our hydroboration oxidation, okay? Now, as I mentioned, this isn't the only place where we're going to see peroxides. But it's just one of those things in case you're on the MCATs, and this is the one question that's going to make or break your career as a doctor, right? It's like, well, we wanted to accept you, but you don't know what a peroxide does. Right, okay. Okay? So one of the things that it does, we add things to the less substituted side of an alkene. Got it? Now, what did I say about this when I introduced it to you guys for the first time? We would come back later and learn the mechanism, right? So guess what we're going to do now? Learn the mechanism. So a peroxide, okay? A peroxide is not a very, like oxygen doesn't really like to be bonded to another oxygen, okay? So peroxides break apart fairly easily into their individual radicals, okay? So if we have this reaction here, oh, I don't know what's wrong with me here, I can't draw. I think I'm just tired. It's been a long semester, right? End up splitting that oxygen-oxygen bond. Where we have our two of our OH radicals. Okay? Well, OH radicals are particularly nasty. They're pretty much going to go after everything. That's why oxygen radicals get formed pretty darn quickly in your body. Okay? You guys breathing in oxygen's not all that nice of a gas. It really wants to react with everything, right? But fortunately, we kind of have some systems in place to kind of protect ourselves from that, right? But not too uncommon for your body to form radicals. So that O radical is going to go look after going to go find the most reactive H that it can. Okay, where's the most reactive H? Where's the most reactive H?
Is it the acid?
Huh? It's the H that's bound to the HBr, right? So here's our initiation, right? Now we got to turn a radical into another one. put a minus there, habits. Okay? So we end up making water, right? HO plus H, right? Water. And a bromine radical. Figure out someday why my computer does that. So continuing on here. Let me try this a little bit differently. So yeah, you can sit up front. Sorry, just remind me, I'll draw bigger for you. I don't think about it. I'm sorry. So watch. So what does this step do? Okay? What does this step do? So our bromine gets added to the less substituted side because it forms what? The most substituted intermediate. Got it? So it has nothing really to do with necessarily the bromine being added last. It adds to the less substituted side to form the more stable intermediate. That's not that big of a shocking revelation, is it? That's how all of organic chemistry essentially works, right? Then we just finish this off, right? We find another hydrogen. So here's our termination. Okay. Good. And I give myself a 9 out of 10, right? Don't forget. Carbon, carbon. Alrighty. Okay, so that's essentially the end of this chapter. That's really all we need to know out of the radicals there. 3 steps to a radical mechanism. Treat your intermediates for radicals, essentially the same as carbocations. And we need to know the difference between NBS and BO2, and where we would use either of them, for instance. Cool. So that's a good stopping point. That gives you guys 10 minutes. Okay, I guess you guys can go run an extra mile or something. Get that workout in when you can, right? So there we go. We'll pick this up on Wednesday and Friday. We've got a couple of things to kind of polish and clean up, and then we're done. I'll see you guys.